in previous class I was teaching you about rectifier circuit. Then the circuit. Okay. Now in previous class you had seen, suppose input AC voltage, if it is given to a rectifier circuit, then the output of this rectifier circuit, it is pulsating DC. Pulsating DC nature. Okay. Now the ripples can be removed. In pulsating DC, both AC as well as DC components both are present. Okay. So in order to remove the ripple, we are again connecting one filter circuit. Okay. So the output of this filter circuit, it is DC in nature. Okay. So here the output of this filter circuit, it is very less ripple. So here AC component is minimized or is removed. So how AC component is removed? AC component from this pulsating DC, it is removed by using filter circuit. Okay, but you see this DC voltage, this is the DC output of the filter circuit. Okay, so this DC output voltage, it varies with this input AC voltage as well as the variation in the load resistor. So we can write this filter circuit, suppose this is RL, okay, and we are taking DC out across RL. Okay, now the voltage here, it is DC in nature, complete DC, that is ripple free. Very less ripple is present in the output of this filter circuit. Okay, so this DC is produced. Now this DC, value of this DC voltage, this output DC voltage, it varies with the variation in the AC input voltage as well as with the variation in RL. Okay, but nowadays we want a fixed DC supply. Okay, so how we can achieve a fixed DC supply? Fixed DC supply means this V naught, this V output, it should not vary with the change in output load or with the variation in the AC input voltage. So how this can be achieved? This can be achieved by using voltage regulator. So we have to connect one voltage regulator. So the output of this voltage regulator, it is always fixed. So this V output, it will not depend upon the load R with the change in RL as well as with the variation in AC input voltage. Okay, so this is the use of voltage regulator. So nowadays this fixed DC supply is generally used in many applications. Means this V naught, it should not change with the variation in load resistor and with the variation in AC input voltage. Okay, so we will study about voltage regulation in this class. So before studying voltage regulation, we will study about Zener diode. So we have studied earlier about PN junction diode. Okay. So a Zener diode, it is similar to PN junction diode, but the concentration of impurity atoms here, the concentration or doping level of impurity atom is very large. Okay, a Zener diode, it is also a PN junction diode, it is also a crystal diode, but the concentration or doping level of the impurity is very high in case of Zener diode. Okay, so this is a special purpose diode. Zener diode, it is a special purpose, special PN junction diode or special crystal diode that generally works in reverse bias condition. Okay, it is having application in reverse bias condition. Okay, so we will see its characteristics in forward bias as well as reverse bias case. Okay, so Zener diode, we can represent Zener diode like this. This is anode and this is cathode. This is the symbol of Zener diode. Okay, and the symbol of normal PN junction diode, it is like this. This is P side and this is N side. This is anode and this is cathode. In case of normal PN junction diode, this is bar. Okay, and this bar, in case of Zener diode, it is replaced with this symbol like Z. Okay, like this Z. Okay, so this is the symbol of Zener diode. Then we will see the VI characteristics. Suppose this Zener diode, if it is made up of silicon semiconductor material, then its forward characteristic will be just like silicon PN junction diode. VF, this is VR, reverse bias voltage, this is forward bias voltage, this is I, reverse current, and this is forward current. Okay, now okay, and this is represented as VZ. Okay, and this is breakdown voltage. Okay, so the VI characteristics of a Zener diode, it is just similar as PN junction diode in forward bias case. Okay, in reverse bias case, see, if we are increasing the reverse voltage, then after this breakdown voltage, that is, this is VZ, it is represented as the breakdown voltage. So after the breakdown voltage, a sharp increase in current is observed. So this is the sharp increase in current. Okay. So generally Zener diode, it is generally used in reverse bias. Why it is used generally in reverse bias case? For making Zener diode as in regulator. Okay. Okay. So this is the VI characteristics of Zener diode. VI characteristics. Of a Zener diode. Okay. Then we will study about reverse bias breakdown mechanism. Okay. See, a Zener diode generally operates in reverse bias condition. So in reverse bias condition, breakdown occurs due to two phenomena. First one is due to avalanche effect, and second is due to Zener effect. So due to these two effects, breakdown occurs in any normal PN junction diode or Zener diode due to these two effects. Okay. So after breakdown, a sharp increase in current is observed in the reverse bias condition. So first of all, we will study about avalanche effect. Suppose a PN junction diode, suppose this is P side and this is N side. Okay. And so in P side the majority carriers are holes, in N side the majority carriers are electrons. Okay. And say this is depletion layer. This is the width of the depletion layer. Okay. Now suppose due to the increase in temperature, minority carriers, say electrons in this P side and holes in this N side or in the depletion layer. Okay. It like this is P side and it is connected to negative potential of the battery. Okay. So this is in reverse bias case. Okay. So with the increase in temperature or at room temperature, some minority carriers, these are minority carriers, suppose electrons and this is hole, these are generated due to the increase in temperature. Okay. So with the increase in temperature, some minority carriers are generated in the depletion layer. Okay. Now due to the reverse bias, that is negative terminal of the battery is connected to P type and positive terminal of the battery is connected to N type. Now due to this the electrons which are minority carrier in the depletion layer. Okay. So it will be attracted towards the positive terminal of the battery. Okay. So it will gain a very high energy. This electron will gain a very high amount of energy, and this electron it will break. Suppose silicon atom, so it will break the valence electron. It will break this electron, which achieves a very high amount of energy. So this electron it will move very fast, and it will break this electron, valence electron, from the semiconductor atom, and this electron it will be released free, so it will become free electron. Okay, so once this electron is removed from this valence band, so now this is free. So again this free electron it will collide with another semiconductor atom. Okay, and again it will release the valence electron and make this valence electron as free electron. So in this way, a avalanche or a group of free charge carriers are available. Okay, so due to the presence of, or due to the avalanche of free carriers, due to the presence of a large number of free carriers, a very high current is observed just after the avalanche breakdown. So this is due to avalanche effect. Okay, so avalanche effect it occurs generally for less doped semiconductor. When the doping level is less, then we are seeing avalanche effect in that diode. Okay, so due to this avalanche effect, a very large amount of current is observed just after the breakdown. Okay, then second effect is Zener effect. Second effect is Zener effect or Zener breakdown effect. Okay, so because of Zener breakdown effect, a very large amount of current is observed just after the breakdown due to Zener breakdown effect. So we will see again. This sharp increase in current, suppose this is VR and this is VF, this is IF and this is IR. So just suppose this is VZ. Okay, VZ is Zener breakdown voltage. Just after this, just at this voltage, a sharp increase in current is observed. Before this, IR it is approximately equal to 0. It is in the range of microampere or picoampere range. So it is approximately equal to 0 before VZ. But after the breakdown, a sharp increase in current is observed. So this is due to either avalanche effect or Zener effect. So we are studying Zener effect. So how this current increases sharply. So due to Zener effect we are saying. Now see, and Zener effect, this occurs due to heavily doped semiconductor. When the level of doping concentration it is very high, then we are saying that the breakdown it occurs due to Zener breakdown effect. Suppose this is p side and again this is n side. Majority carriers are holes, and here the majority carriers are electrons. Okay. Now suppose this is, it is connected to n, p, like this. Direction of the electric field is from positive to negative, and here this is the direction of the electric field. Okay. Now this Zener effect it occurs in highly doped semiconductor. So due to heavy dope, the depth of the depletion region, it decreases. Okay. So the depth, with the decrease in the depth, this depth or this distance, that is the depletion region thickness, it decreases. It decreases with the increase in doping level. So this region, this distance, depletion region depth, it decreases due to increase in doping level in case of semiconductor. So in Zener diode we are seeing that the doping level is very high. In case of Zener diode. Okay, so the thickness of the depletion region it decreases. So with the decrease in this thickness, depletion layer thickness, this is depletion layer thickness, a very high electric field is observed, and the direction of this electric field both are in the same direction. So a very high electric field is created when a reverse bias condition is achieved. Means when we are connecting this external battery to this type of semiconductor, then a very high electric field is created across this junction, across this region. So because of this very high electric field, it is very high. It is in the range of 10 to the power 7 volt per meter. Okay. So if this range of electric field is created here, then it breaks the covalent bond due to very high electric field. That is E, it is in the range of 10 to the power 7 volt per meter. The covalent bond it is broken due to this very high electric field. So due to the break in the covalent bond, a large amount of free carriers, that is free charge carriers, they are created. Okay, so So with this large amount of fixed charge carriers, a very high electric current is observed just after the breakdown. So this is the mechanism. This is Zener diode effect. Because of this Zener diode effect, a very high reverse current is observed just after the breakdown. Okay. So if the electric field, this electric field and this electric field, because of this electric field, if the electric field is in the range of 10 to the power 7 volt per meter, then it will break the covalent bond. Covalent bond. Suppose this is silicon atom. Silicon atom, see, it is surrounded by 4 valence electrons. Again, this neighboring silicon atom, it is surrounded by 4 valence electrons. Okay. Now these two, and these two, and again this silicon, these two. These valence electrons are shared. These two valence electrons are shared to make a covalent bond. Okay, but with the when E is approximately in the range of 10 to the power 7 volt per meter, then this will break this covalent bond and make the charge carriers free. So due to this, a very large current is observed in the reverse bias condition after the breakdown. The breakdown voltage, say it is Vz. So if Vr is greater than or equal to Vz, then a very large amount of reverse current, very large value of reverse current will be seen. So this is due to Zener effect. Then we will see the application of Zener diode. Application of Zener diode. So a Zener diode can be used to make a regulator. Okay. A Zener diode is generally used for making a regulator circuit. So what is the circuit diagram for regulator? Suppose this is unregulated DC power supply. Okay, then it is connected to series resistor RS. This is diode, Zener diode, and this is RL. Okay, like this. So this is the circuit diagram of a regulator circuit. So unregulated power supply, it can be replaced with this voltage. Suppose VI, this is unregulated DC voltage. RS is series resistor. This is series resistor. And this is Zener diode. It is represented as Vz and PZM, and this is RL. Across RL, VL output. It is this VL is regulated voltage. Okay, so this is the diagram of a regulator circuit. Okay, VI, this is unregulated DC voltage, and VL is regulated DC voltage. this RS is series resistance, and this is Zener diode, and it is specified by Vz and PZM. Vz is this breakdown voltage, and PZM, it represents the maximum power that it can withstand. Okay. Now see, this is the circuit diagram of a regulator circuit. In this regulator circuit, this is Zener diode. Okay. So this is Zener diode. This Zener diode, it is always connected. It is always connected in reverse bias with this Vi. This is unregulated. This voltage is unregulated DC voltage, and the output of regulator circuit, it is VL, it is regulated voltage. Okay. So the main aim of a regulator circuit is to produce a regulated voltage by using Zener diode. Okay. And this Zener diode, it is always in reverse bias condition. Why? How it is in reverse bias condition? So this positive terminal, it is always connected to cathode. This is cathode and this side is anode. Okay. So it is connected like this. So Zener diode in reverse bias condition. Okay, we are seeing this Zener diode in reverse bias condition. It can only work in stabilizer or regulator. Now, in order to analyze this circuit, first of all, we have to remove this. We have to remove this Zener diode, and we have to measure the voltage across point AB. First of all, how we are analyzing this regulator circuit. Okay. So in order to analyze this circuit, first of all, we have to remove this Zener diode, and after removing, we have to measure this voltage across AB. So voltage across AB, it is equal to voltage across L. This voltage across RL, and voltage across RL, it is equal to VL. Okay. So it is equal to RL divided by RL plus R, this R, into this VI. Okay. Now, if VAB, which is equal to VL, if it is greater than or equal to VZ, that is specified, VZ and PZM. This VZ is the breakdown voltage. So if VAB, this voltage across AB, and if both are equal, VL, both are equal, if VAB, it is equal to VL, and if it is greater than or equal to VZ, then we can say that the diode, that is Zener diode, is in on condition. What is mean by on condition? If this calculated VL, if it is more than or equal to this VZ, then we can say that this Zener diode, it is in on condition. So in case of on condition, this diode, it will be replaced with VZ, this VZ, that is constant voltage source. Now this is replaced with a constant voltage source, okay, by Vz. If this the diode is in on condition, okay. This is the first case, and second case is if VAB. Second case is if VAB is less than Vz, then what will happen? Then in that case, the Zener diode is in off state. Then the Zener diode, it is in off state. So we can remove this. This is AB, point AB. If across AB, if VAB, what is VAB? VAB, it is equal to VL. VL. So if it is less than Vz, Vz is mentioned in the Zener diode. That is the breakdown voltage of the Zener diode. If VAB is less than the breakdown voltage of the Zener diode, then in that case, Zener diode behaves as it is in off state. Okay, so it can be replaced with open. So how you can say that this is in off state? You can, from the VI characteristics, suppose this is VR and this is IR. Okay, in off state, suppose this is VZ. So when VI is more than, when this VL is more than Vz, then only it will behave as a constant voltage source. Otherwise we are seeing that at this place, when VL is less than Vz, suppose at this point very less amount of current is seen, so I is approximately equal to 0. So in that case we can remove this gap. So this is in off state when VAB is less than Vz. Okay, so in this way we can calculate this VAB. So it is replaced with like this. This is Vz. This is in on state. This is in on state. Okay. Now in on state, how we can express IR? IR, it is equal to IZ plus IL during on state. During on state means when VL is greater than or equal to Vz. This is the condition for on state of the diode, of the Zener diode. Then in that case IR, it is equal to IZ plus IL. IL is flowing across RL. IZ is the diode current. This diode current. IR is the current flowing across the series resistor. So we can write Iz, it is equal to IR minus IL. Now how we can express IR? IR, it is equal to VR divided by R, that is voltage drop across this R divided by R. So VR, how you can express VR? It is equal to VI minus VL or VZ. VL or VZ both are same, divided by R. And how we can express IL? IL you can write IL, it is equal to VL divided by RL. Okay, and how we can express power dissipation across the diode? It is equal to Iz into Vz. Iz into Vz, and this power dissipation, it should be less than Pzm. Pz, that is power dissipation across the diode, it is equal to Iz into Vz, and it should be less than Pzm. This is the rating of this diode. That is, the power dissipation across this diode should be less than the maximum power rating of the Zener diode. Okay. Now we will see this example. This is the circuit diagram of a regulator circuit. Suppose this is a regulator circuit. Okay. Now here Vi is 16 volt. This is unregulated Vi, unregulated DC voltage, and this is series resistance. Series resistance is 1 kilo ohm, and Vz of this Zener diode, it is 10 volt, and Pzm, that is the maximum power that it can withstand, it is equal to 30 milliwatt, and this is RL. Okay, so we have to determine VL, VR, Iz and Pz under two conditions: when RL is equal to 1.2 kilo ohm, and B, when RL is equal to 3 kilo ohm. So first of all, we will see when RL is equal to 1.2 kilo ohm, then in that case, what are the values of VL, VR, Iz and Pz. Okay. So just now we told you that we had discussed that first of all we have to remove this. We have to remove this in order to obtain voltage across AB. We have to remove this Zener diode. Then only we can determine the state. So first of all, we have to determine the state of the diode. Determine the state of the Zener diode. So how this can be achieved? How the state of the Zener diode can be known? So VAB, it is equal to, how it can be calculated? It is equal to RL divided by RL plus this series resistor into VI, that is 16 volt. So RL is equal to, say in this case, it is equal to 1.2 kilo ohm divided by 1.2 plus 1, that is 2.2 kilo ohm into multiplied with 16 volt. So finally equal to 8.73. It is equal to 8.73 volt. Okay. Now we are getting VAB. It is equal to 8.73. 8.73 volt. Okay. Now this VAB, voltage across AB, which is equal to VL, that is voltage across RL. Again, it is less than, this is less than Vz. That is the breakdown voltage of the diode. Then under this case, you can see the graph, VI graph. This is I, this is VR, and this is IR, IF, and forward bias voltage. You can see the graph. This is VAB. We are giving VAB is at this point and VZ is at this point. So in this case we have not achieved VL equal to or more than VZ. So it is not in on state but it is in off state. So off state, it is in off state, I will be equal to 0. Okay, so we have to represent this in off state. So in off state we can represent like this. So it will be equal to, it will be open. So the diode that is Zener diode is in off state. Okay, so how we can determine VL? VL, it is equal to, just we have calculated, it is equal to VAB, it is equal to 8.73 volt. It is equal to 8.73 volt. Then how we can calculate VR? VR, it is equal to VI minus VL. So it is equal to 16 volt minus VL, it is 8.73 volt, 7.27 volt. Okay, then we have to determine IZ. What will be IZ? See, this is open, so IZ will be equal to 0. So IZ, it is equal to 0 ampere. Okay, now fourth one is how to calculate PZ. Now if IZ is 0, so PZ it is also equal to 0, because PZ it is equal to IZ into voltage drop, this VAB that is equal to VL. So PZ is equal to IZ into VL. So it is equal to 0 multiplied with VL. So it is equal to 0 watt. Okay. So when RL is equal to 1.2 kilo ohm, when RL is equal to 1.2 kilo ohm, then in that case this Zener diode, it is in off state. Off state means IZ is equal to 0, PZ is equal to 0, okay, and VL is the voltage drop across this RL. So voltage drop across RL, it is equal to RL divided by RL plus this R into VI, and voltage drop across this R, it is equal to this voltage minus this voltage. Okay, so in this way we can calculate. Then we have to calculate all these values when RL is equal to 3 kilo ohm. When RL is equal to 3 kilo ohm, we have to determine again VL, VR, IZ and PZ. Okay, so when RL is equal to 3 kilo ohm, so again we have to determine VAB. Okay, why we are determining VAB? In order to determine the state of the Zener diode. We are determining the state of the Zener diode. Okay, so VAB, it is equal to RL divided by, here RL is equal to 3 kilo ohm. Okay, so RL divided by RL plus R into this VI. So it is equal to 3 divided by 3 plus 1, that is 4 into 16. So it is equal to 12 volt. Now VAB, which is equal to VL, this is greater than, this is equal to 12 volt, and 12 volt is greater than 10 volt. Okay, that is, it is greater than Vz. So the diode is in on state. So we can write the diode is in on state. So if it is in on state, then we can replace this with Vz. So we can replace this diode with Vz. This is 10 volt. Okay, and this is the direction of Iz. So we have to determine VL. VL, it is equal to Vz, because the diode is in on condition. VL, this is VL. VL across RL, it is VL. So VL, it is equal to Vz, because the diode is in on condition. So it is equal to 10 volt. Okay. Then second, we have to see how to calculate VR. VR, it is equal to this Vi minus VL. So it is equal to 16 volt minus VL is 10 volt. So it is equal to 6 volt. Then third is how to calculate Iz. Third one is we have to determine Iz and IL. Okay. So first of all, we can calculate IL. IL, it is equal to VL divided by RL. So VL is 10 volt, RL is 3 kilo ohm. Okay, 10 volt divided by 3 kilo ohm, it is equal to 3.33 milliampere. Okay, so in this way we can determine IL. Okay, now IR, we can determine IR. IR, it is equal to VR divided by this R. So it is equal to VR is 6 volt divided by 1 kilo ohm. So how much it is equal to? It is equal to 6 milliampere. So how we can determine Iz? Iz as IR, it is equal to Iz plus IL. So from this equation we can determine Iz, it is equal to IR minus IL. So IR is 6 milliampere minus 3.33 milliampere. So IR, it is equal to 2.67 milliampere. 6 milliampere minus 3.33 milliampere, it is equal to 2.67 milliampere. Then we can calculate Pz, it is equal to Iz into Vz. Iz we have calculated, it is 2.67 milliampere into Vz, it is equal to 10 volt. So in this way it is equal to 26.7 milliwatt. 26.7 milliwatt, which is less than 30 milliwatt. Okay, this PZM, it is maximum value of power that it can withstand, which is lesser than PZM. So in this way we can analyze any regulator circuit